Okay, Assalamualaikum and good night to my lecturer, Dr. Shahrul. Today, my team will present about the lightning protection system for commercial building. So, my team consists me, Afiq Faiz bin Zulkifli, and our veteran Govindasamy, and lastly Muhammad Azri Al-Thani bin Nor Asri. Okay, first we go to the introduction. So for introduction, the lightning is a natural occurring electrostatic discharge which to electrically charged region both in the atmosphere or with one on the ground temporarily neutralize themselves, causing the instantaneous release of an enormous energy nearly up to 1 gigajoule. Okay, so for Malaysia is one of the highest lightning activity in the world, average in 180 until 300 days of average thunder day per annum. So the 80% of the lightning discharge in Malaysia normally exceed 20 kA with potential energy around 50 until 100 MV. It was recorded that up to 50% of stroke in Kuala Lumpur exceeds 36 kA compared to the worldwide only 28 kA. So basically Malaysia is the highest the lightning strike. Then we move to the methodology and design. So our designing in lightning protection basically depends on the BSEN slash IEC 62305 and IEEE dash 80. So basically we have four level for lightning protection So level one we have max current 200 and minimum current is 3. So second stage we have 150 kA and minimum current 5 kA. And stage 3 we have 100 kA current for maximum, and for the minimum we have 10 kA. And lastly stage 4 we have 100 for maximum current in kA, and minimum current for lightning protection in stage 4 is 16 kA. Okay, okay. So actually, we have four type of flash lightning strike to consider when designing lightning protection system. We can be seen as below. So basically, we can see here for the figure, we have S1, S2, S3, S4. So basically for S1, the strike flash to the structure, and the effect is a fire and or explosion due to the heat emitted from the lightning architecture. And for the S2, as we can see at the figure, S2 is outside the building, which is flash near to the structure, and the effect will be failure and malfunction of internal system due to the over voltage induced on connected line and transmitted to the structure. And for the S3, the strike will flash to the surface near the structure, and it may cause the injury to the people due to the touch voltage inside the structure caused by lightning current transmit through the surface. And then lastly, for S4, it will flash to near a surface connected to the structure, causing and the effect will cause the failure and malfunction of internal system due to overvoltage induced on connector lines and transmitted to the structure. Okay, so we move to the next slide. So basically here is the lightning flash lightning protection zone. LPZ is introduced in this figure. So we have LPZ, OA, OB, LPZ1, 2, 3, 4. So actually LPZ OA is coverage for external zone and protections against direct flash, full lightning current, and full magnetic field. For LPZ OB, which is cover for external zone, but is not direct flash, it's only a partial lightning or induced current. For LPZ 1, 2, 3, 4, the it will coverage for internal zone, which is no direct flash, partial lightning, or induced current. For LPZ2, also no direct flash in this current, but further dampened magnetic field. And then for LPZ3, as we can see at the figure, it also coverage at internal zone, and also it will protect against the no direct flash, induced current, and further dampened magnetic field. And the lastly, which is LPZ4, also covered for internal zone. It also protection for no direct flash, induced current, further dampened magnetic field. So we move to the next slide. So I will pass to the Azri to explain for the next slide. Thank you.
Okay, Assalamualaikum. My name is Muhammad Azri, and we continue the presentation of this project. So, this part, before we design the grounding system for the building, at first we will do the risk assessment for the building, which from the start we will do the identify the source, identify the structure, which like where's the structure located, and then what kind of surrounding structure it is in the area, and also how many people will be inside the structure. Those will be taken into account when we identify the structure. And then once we identify the structure, we identify the type of loss relevant to the structure to be protected, which we call RN. Inside Rn, there will be R1, R2, R3, and R4. R1 is risk of loss in human life. R2 is risk of loss of service to the public. R3 is risk of loss of cultural heritage, and R4 is risk of loss of economic value. And then we will find a tolerable level of this RT. Then when we have the RT, we will calculate the risk component, Rx, and then we will compare the Rn to ensure it is below the Rx. Once it is below the Rx, the structure is adequately protected. So here is the example of the assessment of LPS in the building, where our complex is called Hijau Kuning Complex, Hijau Kuning Mall Road. Here we have with a length of 50 times 56 meter. That's roughly around 30,000 square feet with a height of 17 meter, which around 4-story building. And in this building that didn't have tower height or chimney present. So danger of people is a medium risk of panic, which is this building normally will normal commercial building, and we targeted it normally will be less than 1,000%. And occupation of the structure, we forecast that the structure as since complex, it will be normally occupied. Thus, when we set the lightning conductor to lightning protection level 1, the electrical incoming will be underground cable from TMB, tapped to the TMB. The active location of the structure, this structure is surrounded by high object or trees, which is what we mean is this structure, the area surrounding of the structure have high-rise building also and tall trees. And then there's a fire risk, but this is a normal ordinary fire risk because this is not what you call factory or something. It is just a normal commercial. And normal service also present in the building, which is gas and water. And the surge arrestor will be designed is impulse around 12.5 kilo ampere. So thus the result of the assessment is risk of human loss is acceptable, risk of loss of service is acceptable, and risk of loss of cultural heritage also acceptable. So first we'll design the mesh grid procedure. And step 1, we will checking the soil resistivity. There are a few methods for checking the soil resistivity, and one of them is the Weiner method. But we what we can calculate is we share what already we calculated and present in other papers also, and this is the value, which is rho is rho first is the 27.21 ohm meter, which is the soil resistivity for the earth, and then for the surface layer rho s is 1000 ohm meter. So The surface layer material, we finding the coefficient CS. Based on this formula, we will get 0.82. And then when we try to calculate the earthing grid resistance with the parameter of length is 50 meters, width is 55.7 meters, and the area, thus we get the area is 27 and 85 meters square. And then we get the total length, which is 55.74 is the x-axis, and we have 54 line in x-axis plus 50 in the y-axis, and we have 8 lines for the y-axis, plus also 54 times 8, which we to find the number of intersection at the grid, and then times 3 is the what we call the earth rod length that will be buried in the grid. So in total we get 4,706 meters. So when we calculate RG, which can be seen in this slide, we will get 0.18 ohm. So in step 4, we will calculate the maximum grid current. So there are a few parameters, which is the IG is the max grid current, IF is symmetrical ground fault current, DF is a decremental factor, SF is fault current division factor, IG is RMS symmetrical grid current. So the first formula actually is IG is 0.34 is the symmetrical fault current times is fault current division factor. We will assume that 34% of fault current will be diverse, so diverse, so hence come with the 34%, which is 0.34. 20 kA, 20 kilo ampere is the symmetrical ground fault current, which this standard we can get from in Malaysia. We check from TMB website, from TMB guideline for the fault current calculation. Thus, for a normal low voltage building, we have a 20 kA, and the IG is actually max grid current times with the decrement factor. So the decrement factor is 1, as we assume is a normal, just 1, times the IG symmetrical grid current. Thus we get total is 6,800 amp. So in the step 5, we calculate for the touch and step potential criteria. For based on the formula, we will get the touch and step potential criteria is test with 70 is what we call, when we assume 70 kilogram of people standing at the area for the earthing grid. Thus we get is 939 volt. And then we calculate for the ground potential rise, GPR, which is 6,800, which is the symmetrical current, times with the 0.18, which we get later we check where we get the 0.18. But we continue, we will get the ground potential rise is 1,224 volt. For the step 7 is the grid design verification, when we will find N. This is, we proceed to the step 7 is because the GPR is exceed the touch and step potential criteria. Thus we need to do the design verification. This is a quite lengthy one, so we start with finding the N, where N equal to NA times NB times NC times ND. With all the formula listed here, we will get N equal to 17.61. And then we will find Ki, which is 0.644 plus 0.148 times multiplied by N, and we will get 3.25. And then we find KH based on the listed formula, we will get 1.09. And then KII based on the listed formula, we get 0.67. Then we will go for the factoring, which is the KM. With this lengthy formula 1, we will get 0.6. Thus we will proceed to the EM. We will get a 73.85 volt. And then since the 23.85 volt is less than the touch voltage from 350 volt, so for the touch voltage criteria is feasible. And then we proceed with the agreed design verification step voltage criteria. First we find KS, the factoring KS. We will get equal to 1 based on the listed formula above. And then we will find ES, which is the step voltage. Based on the listed formula, we will get 226.48. And when we compare to each other, ES will compare to ESTAT in the previous calculation, 226.48 volt is still less than 1023.64 volt. Since both are design our Earth grid design below the calculator design, so the design we can conclude that our Earth design is safe and compliant. And I pass this presentation to my friend Arvin.
Hello. Okay, my name is Arvin and good evening to everyone. Okay, first is design for the lightning arrestor. The protective angle method is a mathematical simplification of rolling square method. The protective angle, that is A, is created between the tips, that is A also, of the vertical rod, and line project down to the surface on which the rod sits. The protective angle afforded by an air rod is clearly a three-dimension concept whereby the rod is assigned a cone of protective by sweeping line AC at the angle protection full 360 around the air rod. The protective angle different with the varying height of the air rod and class of LPS. The protective angle afforded by an air, air, air rod is determined from the standard BX62305. Here we can see two figure. First, I explain about the first figure. The A is the tip of the air termination. The alpha is a protective angle, and H is the height of air termination rod above the reference plane of the area to be protected, and C is the radius of the protective area. Then this is the graph uh, from this road. Then the next slide. Design of the lightning arrestor. For the lightning arrestor, based on the protective angle chart, when we design class 1 protective for 20-meter height of the lightning arrestor, the angle will be 25 degree. Using the basic trigonometry, single lightning conductor will be able to cover for 24-meter diameter. Thus, by comparing with the area of the building, the arrangement will be 3 times 2 as per drawing below. Then the star is mean for the lightning down conductor, and the dotted line is the bare copper tape. Then this one is a internal LPS for building. As the internal building LPS, for each room will have designed copper bus bar for the earthing system. This is the typical room, which we can see there is a copper to earth and clean earth to earth bar. Then this one we can see from this figure, we can see that earth terminal, earth disconnect link, and the interconnecting earth cable. As for the internal building LPS, each room will have designed copper busbar for the earthing system. Aside from that, protection device also will be installed at each electrical box. The typical connection diagram for each board as we can see here. Okay, this one is for LPZ0 and LPZ1, LPZ2, and LPZ3. So in the conclusion, this paper addressed a few and recent development of process in lightning protection system, that is LPS, on normal application. All electrical equipment in an electrical system need to be protected from voltage surge. The rating of the arrestor, the class of the arrestor, and the location of the arrestor all play in a part in this surge protection. In tall building ground is used to discharge, and in sheep water is used to discharge the voltage. In protection of substation, we use different class of lightning arrestor to protect the electrical equipment. Thank you.
And and thank you for seeing. That's from all of us. Thank you.